So welcome to the Picture Language Seminar. We're very pleased today to have Elizabeth Crosson. Before joining the faculty at the University of New Mexico, Elizabeth was a student at the University of Washington, but spent a great deal of time at MIT and worked with Aram Harrow and other people there. Afterwards, she was postdoc at Caltech and will talk to us today about the sign problem and its relation to the spectral gap of quantum many-body systems. So, Elizabeth, it's up to you.
Thank you very much, Arthur, for the invitation. I'm excited to speak to this audience. Let's see, sharing my screen here. Okay. So I know this is a broad audience with a lot of mathematical physicists, and so my talk today is going to be, I'll mention some new results we have in this latest preprint, and you can also consider this kind of a gateway to this larger topic of the sign problem and how it intersects with quantum algorithms. Okay, so starting off here, just kind of a very high level overview. So what is the sign problem? So for me, the central definition is that it refers to the general case of path integrals in quantum physics that involve interference between paths that have different phases associated with their amplitude. So the special case of models without a sign problem are those for which we can define Euclidean path integrals over a non-negative measure. So when I say Euclidean path integrals, I'm talking about thermal equilibrium states, or maybe if you take the limit, then ground states as well. And surprisingly, many natural systems of interest do not have a sign problem. So they have this special property that their path integrals are over a set of paths with non-negative amplitudes. And one reason this happens is that at the level of fundamental physics, the sign problem really arises from the existence of fermions. But this talk is not going to deal so much with fermions. Rather, it's going to focus on quantum spin systems that involve interactions between qubit degrees of freedom. Because this is the main sort of focus in quantum information. And so for this case of quantum spin systems, the sign problem can be characterized in terms of properties of the Hamiltonian matrix. So there's a whole bunch of associated properties that all kind of turn out to be equivalent or unified by this idea of path integrals over a non-negative measure. And in fact, everything I do today is going to be finite dimensional and discrete. So when I say path integrals, they're really just going to be sums of a large number of paths. So of course, for these qubit systems, how do you get these interactions that have a sign problem? Where do they come from? So they can arise as effective interactions between molecules and descriptions of quantum matter. They can also be engineered in real devices, and they can be abstractly simulated. Maybe we can learn their properties, even if they're entirely fictitious, we could simulate them with a quantum computer one day. Okay. Yeah. Okay. So what is this property of the Hamiltonian that captures the sign problem in the case of quantum spin systems? Well, we call them, in modern terms, stochastic Hamiltonians. Okay, so bear with me. I'll explain the term as we go. So let's think of a Hamiltonian H equals the sum over I of HI. So it's a local Hamiltonian. So each HI involves, up to K of the qubits interacting with, say, Pauli matrices, right? The whole space has this tensor product structure of qubits. Okay, so this Hamiltonian is stochastic if in some local basis, local with respect to the tensor product structure, the terms HI all have off-diagonal elements that are 0 or negative, okay? So the off-diagonal matrix elements are real and non-positive. And we're demanding this property for each local term of the interaction. So of course that means it applies to the entire matrix as a whole. Okay, and where this property is going to have special consequences, as I said, this is in equilibrium states. So the ground state and Gibbs state. And we're going to see that these equilibrium states are on the border of quantum and classical computational complexity. So these are standard definitions of the quantum Gibbs state, the quantum partition function, and then if you take the limit as the inverse temperature goes to infinity, then you'll project, let's say that we have a unique ground state. Okay, so let's begin unpacking the consequences of this definition. So if the Hamiltonian has all real and non-positive matrix entries in a particular basis, just for easing this argument, let me also make that true for the diagonal entries, although we can always kind of add something proportional to the identity to make that true. Okay, so let's expand e to the minus beta h as a Taylor series, and we'll see that each matrix, right, so minus beta h here, h has real and non-positive matrix entries. So this here, this matrix has all non-negative entries, right? And you can see that that will be true for each term in the Taylor series. And so this limit of this series, right? So this series has to converge to a matrix with non-negative entries. And so this also means that you could take this limit to project onto the ground state, again, assuming it's unique. And this ground state density matrix, ground state meaning the lowest energy, will also have non-negative entries, at least for some choice of global phase, right? You could make them all non-positive, but let's just make them non-negative by convention with the global phase. Okay, so the fact that the principal eigenvector of a matrix with non-negative entries can be chosen to have non-negative components in the vector is really the central content of the Perron-Frobenius theorem. So you know, this is kind of like a quick and easy proof argument for that. But Perron-Frobenius also gives us a little bit more in general. So it also says that if H is irreducible as a matrix, then the components are strictly positive. So this is the property that the ground state wave function has no nodes. And of course, in general, if the Hamiltonian is reducible, then the ground space will at least be spanned by wave functions with non-negative amplitudes. So one thing I want to point out, of course, stop me anytime to ask for clarifications. But one thing I want to point out is that the stochastic property is so far a property with respect to a given basis. Okay, so let's get an example, some familiar examples up here. So let's think of a spinless particle in one dimension, and let's work in the position basis, where I've written out kind of a discretization of the kinetic energy operator as a matrix, okay? And you'll see that indeed, so everywhere, so it's a tridiagonal matrix, and away from the tridiagonal, you know, you have all zeros. And so indeed, all of the off-diagonal matrix entries are either 0 or negative. And in fact, you know, here I've illustrated some ground state wave functions corresponding to, you know, this Schrödinger equation that are solved typically in a first-year quantum mechanics course. And indeed, you see that the ground state wave functions are non-negative and they have no nodes. And in fact, this can generalize to the case of multiple particles, right? So, so if I had many particles, or if I had a higher dimensional Laplacian, nothing about this argument would change, because in the position basis, as long as their interactions are via this scalar potential only, then we will still have that all the off-diagonal matrix entries satisfy the property. And so in fact, any system of interacting bosons or distinguishable particles that is written as a sort of standard kinetic energy plus a scalar potential is stochastic and does not have a sign problem. Okay.
Quick question.
Okay. Yeah, sure.
What do you mean by node?
Node would be the wave function being 0.
Thanks.
So, yeah. So it has support everywhere in these cases.
So is
Great.
this the case also if you have positive randomness on the diagonal and you get localization?
Yes, it'll still be the case. And what will happen is the wave function will localize, but away from that localized region, it'll be exponentially small, but never truly 0.
Great, thanks.
Yep. Okay, so now kind of returning to the spin systems that are my main interest. So one thing I like to point out is that all of these exciting experimental qubit devices, at least that I'm aware of, are all implementing effective Hamiltonians that are stochastic. Okay, so some of these platforms you may have heard of: trapped ions, neutral atoms, flux qubits, superconducting flux qubits. These tend to implement these quantum transverse Ising models. Okay, and to see that this transverse Ising model is stochastic, you choose the Z basis. Okay, so you choose the Z basis. Your diagonal, right? These guys will be diagonal. Kind of the standard computational basis in quantum computing. So you see that the ZZ part is on the diagonal, the Z part is on the diagonal, and the off-diagonal terms only come from this Xi. And so if all these gammas are negative, then indeed all the off-diagonal matrix entries are immediately 0 or negative. And it turns out if some of these gammas are positive, then you can just do a very simple unitary rotation, conjugating by Z, to flip them to negative, right? So we only require that there is some choice of local basis that you can find that makes the property hold. Okay, just to mention a more general case, I'm sure we all heard about the quantum supremacy result that Google announced last year based on a processor that they codenamed Sycamore. Well, here's what the Hamiltonian from their paper looks like. It's what's called an XY model. It happens to be on a square lattice, which is a bipartite graph, and that prevents these terms from being frustrated, essentially. And so again, if we work in the Z basis, there's always a local unitary transformation that makes these XY models on bipartite graphs, they're also equivalent to, they're dual to Bose-Hubbard models, that these are all stochastic. And so this is a good point to point out, this is a good time to point out that the real-time evolution generated by these Hamiltonians, as opposed to Euclidean time, so the real-time evolution is universal for quantum computing. The complexity of that real-time evolution is not limited in any way. It is only the equilibrium states that come from the Euclidean path integrals that have these semi-classical features. So by pointing out that these devices, yes.
Is it okay? Yeah.
Yeah.
So you have those white terms. So the off-diagonal elements could be imaginary. Is that okay for stochastic?
So if you had general combinations of sigma y terms and you had those imaginaries and you couldn't remove them with a local change of basis, then you would no longer be stochastic. You would start to have a sign problem. Now, in this particular case, this xx plus yy is a special form that is related to a swap operator. So if you actually work out this matrix, kind of because of the product of two y's, there turns out to be no imaginaries. And so I agree it's not immediate to see it. You have to work it out a little bit, but this guy will indeed have the property of real and non-positive off diagonals. Okay. So again, it's no major deficiency of these devices that they rely on these models, but I'm mainly showing you this to show how sort of ubiquitous these models are in practice. Okay, so now getting to kind of the core of that definition I gave, talking about path integrals. So here we can expand the partition function by definition, right? So here's writing out the definition of the trace. And here I'm taking, preparing to create a path integral by dividing by L and raising to the power L. And then I just insert many complete resolutions of the identity in between these various factors, e to the minus beta h over L, and then I get this. And this is what I call a discrete finite dimensional path integral, and that usage is becoming pretty standard these days. So, we're a sum over discrete paths, where our paths you could think of as bit strings, right? Those qubit examples I gave you were in the diagonal in the z basis, and we could think of those as spins being up or down in the z basis, or in quantum computing we think of them as 0 and 1. So, so we're taking a sum over paths. Each xi is an n-bit string if we have n qubits, and each path is associated with this product amplitude. Now, since sort of the analog of the propagator in this discrete path integral is a non-negative matrix, right? We went through that for any beta, so L here is just a large positive integer. This means that every path makes a positive contribution to this sum. And so we can actually define a probability distribution over these paths just by normalizing this density. And well, a reason to do that is that you see that some paths become more important than others, right? What was kind of the core idea behind Feynman's path integral formulation is that, all possible paths are contributing to the amplitude with various phases. But in this formulation, you see that, some paths tend to dominate the path integral. And all of these stories in physics about sort of instanton calculations, this property is lurking in the background. Anytime you can reduce a huge path integral to a sum over relatively few paths, that means that some of them are standing out as more important. And just focusing on those is enough to approximate this partition function. But in the more general case, where these could have complex amplitudes, then no small number of paths could approximate the partition function, because you would inevitably have to add up many, many, many of them to see how the cancellations work out. Okay, so there are a lot of applications of this property. I'm going to focus on a computational one a little bit. So this leads to a classical algorithm called path integral Monte Carlo, which is a classical simulation algorithm based on doing importance sampling on these paths. So this idea really goes back to Suzuki in the 70s. This kind of emphasis of the idea, where he used it to create dualities between quantum and classical models, and to propose this path integral Monte Carlo simulation algorithm for computers. So let me just let me go through these calculations. So here's our probability density. So again, these are n-bit strings. So what we want to happen is that for any given path, we can kind of efficiently compute the amplitude of the path. And so some of the standard steps that go into that, you can split your Hamiltonian. Say we have a transverse Ising model, you can split it into this z part and this x part. And then you'll see that the whole amplitude, again, right, so the z part of the Hamiltonian is diagonal in the chosen basis. So stochastic Hamiltonians depend on a choice of basis. Well, so do path integrals, right? Behind every path integral is lurking a choice of basis, those resolutions of the identity that you insert. That's why they go together. So anyway, so this large factor can just be pulled out immediately because they're all diagonal, and they can all be combined into one exponential. And then meanwhile, we have this kind of product form here of these off-diagonal terms, okay? And again, this is just, if you've seen Suzuki's quantum to classical mapping before, often it is taught as, oh, this is completely general. But in fact, it only works for these stochastic models. It just so happens that many models are stochastic. So sort of the next step involves massaging this off-diagonal part of the path integral. And what you end up finding is that, you have your original spatial system, and that's kind of this part. And you have this new imaginary time direction, which you can think of as a, well, you could take your original d-dimensional quantum model and expand it into a d+1 dimensional classical model, such that as you continue doing algebra on this, you can write your original quantum partition function or your quantum Gibbs distribution in terms of a classical partition function and a classical Gibbs distribution. Okay, so the main thing I want to say is that at the end of the day, you basically get if you start with one of these quantum transverse Ising models, you expand it out into a classical Ising model with, non-trivial interactions in one higher dimension. So the key thing that this can give you is the ability to have an algorithm, right? You could just do classical Markov chain Monte Carlo on the classical spin system and use that to approximate the quantum partition function. This doesn't say it's always going to work, but at least it is always possible in principle. So this is, and in fact, the method works very well in practice, and there are some cases where we can prove that it works. And so when you're considering these equilibrium states of stochastic Hamiltonians, you have this very important special classical simulation method that you can apply to this. Okay, so now I'm going to tell you about a quantum algorithm, one of the most well-known quantum algorithms, and I think one that is appealing to physicists, and it is called the adiabatic optimization. And so it is proposed as a heuristic quantum algorithm that aims to minimize some real valued function on the space of n-bit strings. So this is the problem of combinatorial optimization in computer science. And so this algorithm proposes to do this by remaining close to the instantaneous ground state of a parameterized Hamiltonian. Okay, so continuous one parameter family of Hamiltonians, such that the ground state of H0, when s equals 0, is easy to initialize. And when you get to H of 1, it is actually just your original function, kind of the operator form of that function, so that the ground state of H of 1 is actually the bit string that minimizes your function, right? And so the idea is to slowly change this parameter s, slowly change this parameter s from 0 to 1 and remain close to this ground state. So what determines whether the runtime of this algorithm, well, it can be characterized in terms of this many-body spectral gap. So this is, so this delta here is the minimum over all s in this interval of the difference between the lowest energy and the first excited energy. And here I'm essentially assuming that the ground state stays non-degenerate. And the reason for that is nearly all functions of interest are not going to have the kind of symmetries that would create degeneracy. But the reason I call this a many-body spectral gap, and this is an important distinction related to the title of my talk. So in mathematical physics, a spectral gap is often treated as existing in the thermodynamic limit, right? A system has a spectral gap if, as n goes to infinity, there's some finite gap above the ground state space. In quantum information, we kind of, we stay finite dimensional, right? We work in the asymptotic limit of n, but we don't actually take the limit as n goes to infinity. So when I talk about the spectral gap, what I really mean is the scaling of the spectral gap as a function of the number of qubits. Okay, it doesn't mean that there's going to be a non-zero spectral gap in the thermodynamic limit. Okay, and so this spectral gap is a function of n, and various adiabatic theorems guarantee that the algorithm will successfully remain close to the ground state as long as the total evolution time is some polynomial in n and this inverse spectral gap. And so in theoretical computer science, an algorithm is efficient if it runs in polynomial time in the size of its input. And so if this delta if this delta is at most inverse polynomially small, then this is the case where the algorithm is efficient. Okay. Now, so far I've talked about this in general as this parameterized family of Hamiltonians. And so far we've only fixed the endpoint, and we've demanded, well, we fixed the final endpoint as the function we want to optimize, and the initial endpoint should be something simple whose ground state we can prepare. But other than that, we can consider various Hamiltonian paths with the goal of making this intermediate spectral gap as large as possible, maybe also subject to hardware constraints on some device. And so the original proposal for this algorithm is what is called transverse field adiabatic optimization. So here, so this is by far the most well-studied version of this algorithm, where we take a simple linear interpolation between a uniform transverse field, just a sum of one local x operators, and the final Hamiltonian of interest. Okay, so that's the proposal. But given everything we've just seen, we know that these transverse Ising models are stochastic Hamiltonians. And I'll just mention here that for complexity theorists, the stochastic local Hamiltonian problem, estimating the ground state energy, has a limited complexity. It's in the third level of the polynomial hierarchy, but also more familiar to many of us are these classical simulations based on Monte Carlo, and these are effective in practice. So I should say that this algorithm was proposed around the year 2000, and it was kind of a catalyst for a lot of these realizations about stochastic Hamiltonians later in that decade, right? So the algorithm was proposed, and then these kind of limitations were recognized. And those limitations also motivate the study of adiabatic optimization with non-stochastic Hamiltonians, which is what I'm going to analyze here. So this algorithm, hopefully it sounds compelling. It sounds like a very nice story. Wouldn't it be great if we could sort of follow these physical ground states and use it to do optimization? But a lot of negative results have been found about this algorithm. So it motivates considering generalizations. And when we consider non-stochastic, so models with a sign problem that don't have the stochastic property, it turns out that adiabatic computation can actually be universal for quantum computing. So any quantum algorithm can actually be done in this ground state framework, but not the exact one I just explained, because in the more general universal constructions, the final Hamiltonian is not just diagonal in the computational basis. So that's a distinction that's important. There's adiabatic algorithms in general, which can be universal, and there's adiabatic optimization, which is this specific algorithm. Okay, so that's encouraging that if we have a sign problem, we can be potentially universal. And then if you have a sign problem or in your Hamiltonian, then this special property of the path integral goes away, and all that story about Suzuki's Monte Carlo method no longer applies. And so the practically efficient simulations break down. And so today's message is that these non-stochastic Hamiltonians, they do make adiabatic optimization more difficult to classically simulate. But it turns out what we discovered is that moving to non-stochastic Hamiltonians almost always decreases the performance of the algorithm by shrinking the spectral gap. And so we've kind of evaluated this long-time conjecture, and we're sending the message that non-stochastic adiabatic paths are not actually a promising direction for quantum speedup with this algorithm. Okay, and so to make this case, we've introduced a new, or at least as far as we know, a new mapping between systems with a sign problem and systems without. So stochastic and non-stochastic Hamiltonians. Okay, so the original Hamiltonian is just going to be some Hermitian matrix in the computational basis. Okay, and then what we call the de-signed Hamiltonian, this H, so H is going to get mapped to H bar. We're going to leave the diagonal part alone, and we're going to take minus the absolute value of all the off-diagonal parts. So we're just going to entry-wise force them to have the same negative phase. Right, so it's a highly nonlinear mapping. And so for any non-stochastic adiabatic path, we now get a corresponding stochastic adiabatic path, and the endpoints are unaffected by this transformation. So in mathematical terms, remember this, so remember this connection between ground states of stochastic Hamiltonians. Really, if you're, really that is the same thing as the top eigenvector of a entry-wise non-negative matrix. And so this question about the spectral gap of H versus H bar, you could also just ask about the spectral gap at the top of the spectrum for a Hermitian matrix G and its entry-wise absolute value G bar. Okay. And what we observe is that de-signing almost always increases the spectral gap for any reasonable ensemble of Hamiltonians. So any general theorem on this has to be probabilistic because, in fact, we can numerically find exceptions, but the fraction of exceptional cases where this de-signing operation does not increase the spectral gap, the fraction of those cases goes to 0 very rapidly with the dimension of the matrix. So this is one of these statements, this idea that going from H to H bar increases the spectral gap is one of these, appears to be one of these almost always true statements. And then I'll prove some results, but you can tell by the way I'm phrasing it that a lot of what we would like to prove are still open questions that I want to potentially pose to you all. I'm happy to talk more about these. Okay.
I have a question. So
yeah.
you started with the non-stochastic Hamiltonian, and then you come up with another one which is still non-stochastic, but with
no, it is stochastic now.
Okay.
The new one, H bar.
Okay, that is stochastic.
So, yeah, so all the off-diagonal entries are real and non-positive because of this minus sign. So we just kind of we took it and we just basically said, your original Hamiltonian had all these non-trivial phases, and we just forced them all to be of the same phase.
I think you have an extra non there in your slide.
Oh, I'm sorry. I'm not sure. Not sure where it is, but I believe it.
The description on the right, H bar on the side, you're saying de-signed and shifted Hamiltonians are non-stochastic. So that's it.
That's a typo. I'm terribly sorry there.
All right,
okay.
so
Just to make it clear. Okay.
Sorry.
Thank you, and sorry for the typo.
Sorry, I have a question, if I may interrupt.
Yes, please.
I'm confused as to the statement with regard to how general it is that there is a sign problem if you don't have a stochastic Hamiltonian. I'm thinking in particular of matrix quantum mechanical models, which I doubt have a sign problem, as I would think of it, but yet they do not appear to be stochastic because they have complex off-diagonal terms.
Okay, sure. So one thing that can often happen is that there might be some unitary transformation that removes those complex phases, and that when you write up, so I consider the central definition is the one in terms of path integrals. If you can write your model, if you can write, say, the states, express the partition function or amplitudes of interest as these non-negative path integrals where every phase is non-negative, then I would take that as not having a sign problem. And for these qubit systems, the notion of a stochastic matrix captures that. Now,
do you have a theorem that states that there is a sign problem if there exists no basis in which it is stochastic?
Right.
Is it at the level of theorem?
So I would say yes, but one thing that you have to be careful of is how general of a basis transformation are you going to consider? So for example, if you considered non-local basis transformations, you could diagonalize the Hamiltonian and all of its off-diagonal entries would be non-zero, or would be zero, sorry. So the question you're asking, so if you give a qubit Hamiltonian with a non-negative path integral in some local basis, then can the sign problem always be cured? I'm very tempted to say yes, but maybe I should be a little careful. But yes, it's very close to a theorem if it isn't already one already. And this point about the Monte Carlo simulations and this point about the limited complexity, those work directly with the non-negative path integral. And so certainly, I guess that's what I should say, is that the stochastic property certainly implies the path integral is non-negative and captures the cases we care about. But if there's some additional tricks you end up doing to get the path integral to be non-negative, then that Hamiltonian I would still, or that system I would still consider not to have a sign problem. And maybe those tricks are more general than just a basis rotation. Maybe they involve some dualities or something like this. So I should be a little bit careful.
Thank you.
Okay.
I have a question. Can I ask?
Yes, yeah, please.
So you're saying, if I understand correctly, you're saying that stochasticity or non-stochasticity is a property of the Hamiltonian, not of the system.
Sure, it's a property of the Hamiltonian, yeah.
So it's a property of the basis, of your choice of basis. Is that right?
Right.
Selectively, it is
It's
a
not the
chosen
property of the
unit fixed
system.
basis, yeah.
It's not the property of the
That's-
system. If you make a clever choice of basis, then you may not have this problem.
Absolutely. And in fact, there are results that say that it can be very computationally hard to find the basis that makes the Hamiltonian stochastic.
Okay.
Now, most cases of interest, physicists have worked long and hard on identifying these, and usually that is not a problem in practice, right? Usually these are fairly well classified, but you can construct examples where it is NP hard to find the basis in which there is no sign problem. And then conversely, there are systems which we believe, for reasons in computational complexity, kind of the universality of quantum adiabatic computation, tells us that there are Hamiltonians for which there should be no basis, no matter what, no local basis that removes the sign problem. Such Hamiltonians must exist, or these things we believe about the polynomial hierarchy not collapsing would be false. So strong conjectures in computer science imply that there are cases where you cannot rotate into a stochastic basis.
So can I ask a question? In the standard basis, fermions are non-stochastic. What is the situation about arbitrary basis?
Sure. Yeah, certainly in the standard basis, these fermion path integrals have a sign problem. I'm not actually aware of anyone defining. So in quantum information, we often just say qubits are all there is, and we can treat stochastic and sign problem as synonymous. But I think when we have fermion systems, whether or not there is a sign problem maybe depends on something more general than whether the Hamiltonian that describes the interactions just has these matrix properties, right? It's kind of an additional constraint from the anti-symmetry. But there are, so one way to answer your question is that anytime we can do a Monte Carlo method on the path integral, and there are these determinantal Monte Carlo methods for fermionic systems, then in a sense you've tamed the sign problem, because you've got your path integral into a form that is suitable for importance sampling. Some paths are more important than others, so Monte Carlo is possible.
Are you going to go over fermions at some point and why they're so special?
Not really, but to just briefly say it, you know, consider the ground state wave function, right? The fact that you can exchange two fermions and get a minus sign immediately tells you that you've kind of left the realm of this Perron-Frobenius type properties. So maybe that's the quick answer for why that's the case. Okay. All right, so this slide actually just is meant to explain what I was going to get to, so I'll just skip over this and start talking about some properties of this designing operation. And so the initial thing I want to point out is that designing always decreases the ground energy, right? So I'm using a bar for the designed Hamiltonian. And so the original Hamiltonian has energy E0, and here's a quick variational argument that the designed Hamiltonian has a lower least eigenvalue. So you just take your original wave function and expand it in the appropriate basis. And then you propose a new absolute value of that wave function. And what you can find is that the absolute value wave function, together with the designed Hamiltonian, just has a strictly lower energy than the original one. So essentially, if you expand out this you know, matrix vector product here, you'll find that now every single term contributes a negative quantity, right? Because both the vector components are positive and the Hamiltonian matrix element is negative, at least on the off diagonal, and the diagonal is unchanged, so it can cancel both sides. So you've strictly made this smaller, and by the variational theorem, this tells you that the energy has decreased. Okay, so now think of the case where the original Hamiltonian is positive semi-definite, so all its eigenvalues are non-negative, and we can always arrive at this case by adding a large energy shift to the system. So now the trace, the sum of the eigenvalues, is unchanged by the designing operation, right? Because remember, the designing does nothing to the diagonal. So the trace is unchanged. And so if you think about this, you have all of these positive numbers that have to add up to the same value, but the lowest one has gotten smaller, right? And so designing must always increase the spacing between the eigenvalues somewhere in the spectrum. Okay. Now, if we could show that designing raises the first excited state energy, then we would be done. We would just show that the gap always gets bigger. But it turns out that this is not quite true in general. Okay. So let me give you a random matrix argument for this, what designing does to the spectral gap. So, consider an n by n ensemble of n by n random symmetric matrices with IID entries of mean 0 and variance 1. Right? So if the entries are Gaussian distributed, they're IID. This is just the familiar Gaussian orthogonal ensemble. And of course, Wigner showed about 100 years ago that the distribution of eigenvalues of these matrices is a semicircle, depending on, well, the normalization I just gave, between plus and minus root n. And it turns out that this spectral density property in random matrix theory depends on just the first few moments of the distribution from which we're choosing the entries. And so very similar semicircle law holds for entries chosen uniformly in -1 to 1, which will be useful for the argument I'm about to make. Now, since there are n eigenvalues, the typical spacing between them is 1 over root n. I should have a big O notation here. And large deviation bounds for the spacing, kind of Tracy-Weedon bounds here. So we're going to think of this as we're going to focus on the top of the spectrum. I'm going to take the absolute value of these matrices. Anyway, so we understand the spacing here from random matrix theory. So let's think now about what will happen when we take this ensemble of Hermitian or symmetric matrices and we take the absolute value of all the entries. Okay, so so that corresponds to an ensemble of symmetric matrices with non-negative IID entries, say, chosen uniformly from 0 to 1. Right, so we take the -1 to 1 ensemble and we take the absolute value of its entries. So every matrix in this new ensemble can be obtained from a matrix in the previous ensemble by adding a matrix that has a 1 in every entry. So this is a gigantic rank 1 matrix that we've added to mimic the absolute value operation with an additive shift instead. Okay, and so if you think about it, this rank 1 shift, this matrix of all ones has a single eigenvalue of size n, and the rest of the eigenvalues are 0. And so what it does is it takes that top eigenvector and just makes it huge in comparison, right? So we've gone from a gap that is like 1 over square root of n to a gap that is, you know, gigantic in this normalization, right? Going to infinity. Okay, so that's the simplest argument I can give for what designing does in this setting of random matrix theory. And that's basically a complete proof, but in case you want to see how quickly this kicks in as a function of the size of the matrix, so if you go to our paper, there's lots of numerics. We kind of built up this conjecture from doing numerical studies, and then we're able to prove various cases. And so you can see that, so we'll call this the fraction of non-stochastic Hamiltonians that have a bigger gap than their designed counterpart. And you see that this fraction of cases where designing does not increase the spectral gap goes to 0 exponentially with the dimension of the matrix here. And the argument I just gave didn't cover the complex case, but actually the complex case, the asymptotics kick in even faster. So that it's even more the case that this designing almost always increases the size of the spectral gap. Okay, so there's not a whole ton of time, and this later topic is kind of complex. So let me try to give
Can
you.
I ask you a quick question?
Yeah.
Elizabeth?
Yeah, please. Yeah.
So you prove your results assuming, so the proofs of the gap of the stochastic versus non-stochastic, is it with respect to general random matrix ensembles that are dense, or does it actually hold for local Hamiltonians that are generic as well?
Great question. And essentially, all cases of local Hamiltonians are open. So so we have a lot of results in our paper, but these spectral graph theory results at least cover the sparse case. So it's not that our results are only for IID matrices, but that's the only place where we kind of have a complete solution. And when it comes to local Hamiltonians, I consider our results using the spectral graph theory to really just be like a first step towards understanding this. So yeah, one of my main open questions with this is, what about random local Hamiltonians? Let me see. There is one other case that covers some local Hamiltonians. So suppose we have a Hamiltonian that is initially diagonal in the x basis. And so in the computational basis, it will have positives and negatives everywhere. It is not the case that we can just do a rotation to get rid of all the positives and negatives, or to make them all of the same sign. And we do show that in this case, so you take this matrix that is diagonal in the x basis, and you take its de-signed version in the computational basis, then we just kind of show, by a brute force calculational argument, we can show that this always increases the spectral gap. So that case includes some local Hamiltonians, but as you can see, it's quite limited. Okay, yeah, I wanted to briefly touch on some of this geometry. Maybe I'll go like another 5 minutes and then take more questions just to expose you guys to this topic. It might be kind of hard, but okay. So think about a combinatorial graph of vertices and edges. So we can define a matrix associated with this graph, which is the adjacency matrix. And basically, you know, you could consider the matrix as indexed by the vertices, and you're going to put a 1 in each position where you have an edge and a 0 otherwise. So that's the adjacency matrix. And then form this other matrix D as a diagonal matrix with a degree of each vertex along the diagonal. So then the random walk on this graph, the transition matrix of that random walk, right, which is a stochastic matrix, it conserves probability, and it's called the random walk Laplacian. Okay. I guess in this normalization, I called it the transition matrix. I should call it the rate matrix. That's, yeah, the rate matrix. Okay, so sometimes called Q in the physics literature. Okay, so this random walk Laplacian. And the point is that by iterating this guy on a vector, you conserve probability and you simulate the probabilistic random walk on the graph, where, you know, at each step you choose an edge at random and step in that direction. Okay, so the random walk Laplacian can be transformed by a similarity transformation to a symmetric matrix, which is called the normalized Laplacian. And this is the primary object of study in spectral graph theory, although you could study the spectrum of the adjacency matrix as well. And so in general, spectral graph theory connects the algebraic properties of this normalized Laplacian to the geometric properties of the original graph. And because L is a symmetric matrix, it can be directly treated as a quantum Hamiltonian as well. So the ground state of this normalized Laplacian is uniform over the vertices. And these definitions can be generalized in a fairly obvious way to include weighted edges. So you put positive weights on each edge and put positive weights on the vertices. And okay, notice that the off-diagonal entries all come from this adjacency matrix with this minus sign. So not only are these normalized Laplacian symmetric matrices, they're also stochastic Hamiltonians. There's a sense in which, if you maybe use this recent paper as a gateway, you can see there's a sense in which every stochastic Hamiltonian can be mapped to a normalized Laplacian. And really what this subject is all about is, you know, this ground state geometry, this weighted graph that takes into account both the weights on the vertices and the connectivity of the matrix elements, how that relates to the spectrum of this Laplacian or Hamiltonian, if you like. Okay, so let me explain just a simple result actually that I proved a few years ago, and then I'll stop in 5 minutes or less. So it's about an isoparametric inequality for Hamiltonians. So isoparametric inequality involves the measure on the boundary of a set, the ratio of the measure on the boundary of a set to the measure inside of a set, right? And this, I mean, there's the idea of the circle being the shape that in the plane that maximizes the area for a given perimeter. This is an isoparametric inequality that is saturated by circles. So in a discrete space, in a graph space, it can be, you can think of this in terms of what we call vertex expansion. Let me define this boundary of S to be an interior boundary of vertices, right? So here I've talked about a set S that includes all of these vertices, and the boundary of S are the vertices in the set that connect to something outside of it, right? And you can see then that the size of the boundary of S over the interior of S is just 3/4. That's the isoparametric ratio of the subset S. Okay, so let me say how that translates to a quantum setting. So think of the elements of a particular basis as vertices of a graph, and the ground state as a probability distribution on this graph. Okay, so positive weights. And connect two vertices by an edge if they have a non-zero matrix element between them. And actually for this result, it's not going to matter whether the Hamiltonian is stochastic or not. This is going to be a general result. So if the edge is just anything other than 0, we'll put an edge there. And then the boundary of S will be this interior boundary. So it'll be the set of vertices inside of S such that there's something outside of S that you are connected to by an edge. And the basis B could be discrete position, or it could be the computational basis, right? So, so you could think of if you were in a position-like system, you know, and this vertex was your set S here, then, well, maybe take a continuous region, then the boundary of that region would be something that the kinetic energy operator connects you to outside of the set. So it kind of creates an edge to the outside. So here's a theorem, actually, that is completely general. So let E be the ground state energy of your Hamiltonian, let delta be the spectral gap, and use this operator norm for the largest energy. Then what you can show is that for any Hamiltonian, any choice of basis, and any subset within this basis that contains less than half the total probability of the ground state. So you want a subset where the ground state has support, but not the whole thing, basically, less than half. Then you can upper bound the spectral gap purely in terms of this isoparametric ratio of the set S, okay? And then here you have this factor, which, you know, for a typical local Hamiltonian, the operator norm is like n. And so what is, the reason I want to show you this is that it depends on the ground state, but not the details of H. It's kind of been taken into this spectral radius. So for a given distribution, it constrains the spectral gap of any Hamiltonian with that ground state distribution. Okay, so here's a picture. Right, so this quantum adiabatic optimization will inevitably encounter small spectral gaps when preparing complicated multimodal distributions. And this shift to non-stochastic terms does not prevent this problem. Whenever you have subsets of probability with a small isoparametric ratio, it constrains your spectral gap and means that it's going to be hard to prepare them in this ground state manner. Okay. I'd like to conclude so that I don't go over time. I have a few concluding statements about, you know, where do we go next with the adiabatic algorithm? It seems to have a lot of general deficiencies. I think it is most interesting to consider the use of excited states, so some diabatic transitions that enter into excited states. But I think as a research area, you know, we're deciding where to go next. There's this quantum approximate optimization algorithm and so on. The question that was asked, so, you know, the main question we sought to answer is in a sense still open. Prove that for any reasonable ensemble of Hermitian matrices, local Hamiltonians, maybe some specific lattice models you care about, that the entry-wise absolute value, or this designing, increases the gap. Okay? And then, of course, the same question can be asked for comparing bosonic and fermionic systems with the same kind of interactions. Can you create inequalities between the gaps of those? You know, so you could imagine doing something like using solutions of the bosonic system, using relations between the two to learn something about the intractable fermionic system. And that's a fully open direction as well. Thank you.
Well, thank you very much, Elizabeth, for a stimulating talk. I have start with a question. I hope there'll be a lot of questions. Let's see. Well, you have a nice upper bound on the gap in your last example, but we'd like to have a lower bound. And
oh,
you
great.
mentioned in your abstract the Cheeger constant, which is related to the gap in Laplacian. Can you tell us how the Cheeger constant comes in?
Yes, absolutely. So this is the part that I had to skip over at the end, but I can say a bit about that. So I gave you this isoparametric inequality, and it's a very rough upper bound in terms of just the vertices. It kind of abstracts away the edges. Cheeger's inequality gives you some tighter characterizations of the gap. And so so first define this edge expansion. So it just counts the number of edges. So for a subset S, it counts the number of edges going from S to its complement, bar now means complement, divided by the number of vertices in S. So that's the edge expansion. And so actually, it turns out that a lot of this stuff that I just explained for the lowest spectral gap actually works for the whole low energy spectrum. And that is, some low energy excited states. And so define the Cheeger constant, or the K-way Cheeger constant, as you're going to, well, let's first think of the case K equals 2. So for the case K equals 2, we're going to split into 2 subsets that are disjoint. And the idea is that you want to minimize over all possible all possible choices of these disjoint subsets. And then of the 2 of them, you take whichever has the larger expansion. Okay, and in the general case where you have K subsets, you're going to minimize over all choices of those K subsets and look at the one that has the largest expansion. Okay, and this Cheeger constant, this kth order Cheeger constant, actually characterizes the kth eigenvalue of the graph Laplacian. So this is, this result actually is as recent as about 2014, proved by theoretical computer scientists that work on graph theory. So, so what this says is that, so here's the isoparametric inequality direction that I kind of gave you, which says that the edge expansion upper bounds the kth eigenvalue. And indeed, this, my paper with isoparametric inequalities translates this to the quantum setting. But this other direction is more non-trivial in a way, because this gives you a lower bound on the kth eigenvalue. And this is the direction that is properly called Cheeger's inequality, although sometimes the whole thing is. And so you can see that what this is telling you, let me give the intuition, which is that these subsets of low expansion are capturing bottlenecks in the state space. They're like sets, if you think of the random walk on the graph, these are sets that are very hard to escape. They take a long time to escape because they have a large amount of vertices inside of them and relatively few edges leaving them. And it turns out what this says basically is that up to this square root factor, and D max here is the maximum degree, up to these factors, this bottleneck property, this search for bottlenecking subsets, is the if and only if of where the energy eigenvalues come from, right? So you have a small spectral gap if and only if you have this bottlenecking type of subset. And all of that actually applies to the case of graphs with only positive edges. I'll just kind of flash this slide for the signed case. So now the signs can have plus and minus edges. Then these Cheeger constants become modified by an additional quantity called the frustration index. Now it is no longer just bottlenecks that create small spectral gaps. You can have this, what I consider phase frustration, can also control the size of your eigenvalues. So these 2 slides are discussed in detail in the paper that I cite, or the preprint that I cite at the beginning. But both of these are results that already existed before that we kind of adapted to this, quantum designing questions that we had. But just in terms of geometry of graphs, I encourage you to follow that chain of references.
Ramis has a question.
Yes, thank you. Just a quick question on this open problem with respect to local Hamiltonians. Have you done numerical investigations? And if so, does it seem to support the conjecture that the gap gets larger?
Absolutely. So let me let me explain this numerical slide, and glossing over some excessive amounts of detail for the most important parts. So for example, so we did a lot of cases, but especially my co-authors who are proper computational physicists, they wanted to constrain the amount of cases we consider to get good error bars, so they could do like 10 million random samples and so on. So we focused in on a particular set where all of the randomness is actually in this XX part of the Hamiltonian. So we'll have the driver, or we'll have this transverse field part. We'll have this interacting part. We'll always have a ZZ form. And then we'll consider various choices for the alpha ij that can either be plus or minus 1 or uniformly at random. So indeed, this is some ensemble of random Hamiltonians, local Hamiltonians, that is well motivated, say, by experimental constraints. And then we'll ignore this part. And so for that ensemble, let's look at, just make sure I say this correctly.
I think I'm already convinced, but this is
okay.
great.
Okay. Here's the one. Here's the one. Okay, you're already convinced, but you can see that in all but this, 5% or 0.5% of cases, the theorem holds. And yeah, if you just run a quick mathematic on this, you'll see it's overwhelmingly true. And there's also a few stack exchanges about this that came from people I don't know that you can check. And they say, well, this problem seems very nonlinear, so it's probably hard. It's on Math Stack Exchange a little bit in the past few years. So I think it's going to be a very hard problem to resolve, but seems pretty interesting to me.
Can I make a comment?
Sure, thank you.
Yeah, so the p orbital of a carbon should always have a node to have a meaningful chemistry. So this sign problem, but again, it's a fermionic system. So it could be a system dependent property that this stochasticity, if you want to call it, or non-stochasticity.
Yeah, absolutely. I guess this last line that I'm talking about, imagine some fictitious version of this molecule where the electrons were actually bosons. Totally fictitious, but maybe by studying that, you can learn something actually about the fermionic case. As we know, there are these Green's function Monte Carlo methods where if you understand where the nodal domains are in chemical wave functions, you can often get something out of that. So in the chemistry setting, it would be like comparing a real system to a fictitious bosonic version with the same Coulomb interactions. And, maybe that's easier or more difficult, I'm not sure.
Well, if there are no other questions, I'd like to thank you, Elizabeth, again for giving a really nice talk. And
Arthur, sorry. Can I ask one last question, Arthur?
Yes, of course, Dante.
Sorry. Your designing reminds me of Lieb's flux phase problem in fermionic systems. Is there a relation there by any chance?
No, I've never heard of that, but I'm definitely going to look into it now that you mentioned it. This does seem like something that must exist in some form in the literature in the past. So Lieb's flux relation, I'll search
flux,
for.
I think it's often called Lieb's flux phase relation. It's a paper of.
Okay.
It's adding a sign to fermionic lattice problems.
Okay.
Yeah, you'll find it with that.
Sounds fascinating. Thank you.
May I ask you a question?
Yeah, sure.
Okay.
Yeah. So you mentioned the Perron-Frobenius theorem, and I wonder that there is a so-called Feynman no-null theorem, which says that the ground state for bosons has a wave function with no nodes, and it can be chosen to be real. So I wonder if this is the same theorem but a different name, or it's really like two different theorems.
It's absolutely the same theorem.
Oh, I see. Okay, yeah, thank you.
As I learned years ago from Arthur's book on quantum physics from a functional point of view, that started me down these paths.
Okay, yeah, thank you.
Thanks.
Are there any other questions?
Thank you for the nice talk.
Thank you, everyone. Thank you,
Yeah.
Arthur, for the invitation.
So thank you, Elizabeth. And next week, we continue with Matt Hastings. And after that, we also have a number of interesting seminars. We're here at home, and so our normal summer activities don't take place. And I think we'll just continue this seminar as long as it seems reasonable. So thank you, everybody, and goodbye. See you next week.